So this time I'm talking about models with latent random variables. So in the reading, there was a discussion of the variational autoencoder. It was a tutorial to the variational autoencoder. I hope that the tutorial was not too difficult. The original variational autoencoder paper is extremely difficult. So this tutorial is actually pretty accessible. So hopefully people could figure it out. I'm going to run through the content of the tutorial, and I'd like people to ask any additional questions at the beginning part. Then I'm going to talk about some stuff about handling natural language with latent variables for the latter half of this time. But just to give a very quick overview of kind of like a typology of our different models and different variables and stuff. I think everybody, most people in here know this anyway, but a discriminative model is a model where we calculate the probability of the output given the input, P of y given x. And a generative model is a model where we calculate the probability of a variable x, like we were talking about, or we can calculate the joint probability of p, x, and y in USIS for some sort of inference. So quick quiz, which of the following models are discriminative versus generative? By LSTM, part of speech tagger is discriminative. A globally normalized CRF part of speech tagger is discriminative. And a language model is generative, yes, okay. So then, types of variables. There's a lot of terminology that kind of gets mixed up here. For the purpose of this time here, I'm going to make two distinctions. These distinctions aren't super clear in the literature, and people call different things different names. But what I'm going to say is observed versus latent variables. So observed variables are something that we can see from our data. So in our training data, our input and our output are observed variables. And a latent variable is a variable that we assume exists, but we aren't given the value in the training data. I'll explain in a second why this can be confusing. This terminology can be a little bit confusing. But there's also the distinction between deterministic versus random variables. And this is very important to understand this particular class. But a deterministic variable is a variable that's calculated directly from the input or from something given a deterministic function. While a random or stochastic variable is a variable that obeys a probability distribution. And according to that probability may take one of several values. So do people know Schrodinger's cat? So Schrodinger's cat is the idea where the cat is either dead or alive, but you don't really know until you observe it. So that's a stochastic variable. So going back to NLP, what types of variables are these? So let's say we have an attentional sequence-to-sequence model using maximum likelihood estimation with teacher forcing. Given this, are the following variables observed or latent variables and deterministic or random variables? So the input word IDs F are they observed or latent? Observed. And deterministic or random? Yeah, basically deterministic. They're given to us. The encoder hidden states H are observed or latent? Yeah. And deterministic or random? This one was significantly slower, but yes, deterministic. So there's no probabilistic interpretation of the decoder hidden states. We put in our input and we get the hidden states out, and there's no probability distribution over these hidden states. One thing that's a little bit confusing. Sorry, I forgot to clarify this, but Often people will only refer to random variables as latent variables, and you can also refer to like deterministic hidden variables are referred to as hidden variables, but for the purpose here, I'm going to say latent variables. And what about the attention values? These are observed or latent, and deterministic or random. Yes, these are also deterministic. So this is actually a little bit confusing because attention values kind of look like probabilities, right? They're between 0 and 1, and they add up to 1. But actually, they're still just completely deterministic variables. There's no kind of probability involved in them, despite the fact that they look like a probability distribution. And finally, the output word IDs, E. Are these observed or latent? This is kind of a trick question. So at training time, they're observed, right? At test time, you could say they're latent because we don't know the values. And what about deterministic or random? A good.
So if you're using like beam search like that, it's going to be random, I think. But
so beam search is one good thing. It's even better to think about randomly sampling outputs from your model. So you can randomly sample a bunch of outputs from your model where you randomly get the dog ran with a probability of 0.3 by randomly sampling from your model. You can get the dog walked or something with a probability of 0.2, etc. So anything where you can randomly sample a value from your model and get a different one every time is basically a random variable. So the outputs E are random variables. Specifically at training time. At test time, you're given them, so you might call them observed variables, but yes. So keeping this kind of stuff in mind, I think it's worth, I think now we can go on to the main topic, which is latent variable models. I'll start with kind of a reiteration, or I'm going to say a lot of the things that were in the reading, but I'd like people to ask questions that they had when doing the reading, if anything was not clear. So first, why do we want latent random variables? The idea is that we believe that there are underlying latent factors in speech that affect text or images, or latent factors that affect the text and images in speech that we're observing. So, for example, what is the content of the sentence is one thing. Who is the writer or speaker? What is their sentiment? What words are aligned to others in a translation, etc. And the important thing is that all of these have a correct answer to them, but we don't know what it is. So there's no such thing as so let's say, okay, somebody made these slides today. So somebody made these slides today, and it was either me or one of the TAs, right? You can probably guess with a certain probability whether it was me or the TAs, but what it wasn't was for typing these words, it wasn't 0.8 of me and 0.1 of Dan, 0.5 of Max and 0.05 of Max and 0.05 of Hector. It's not a random interpolation between all of us. It's, you know it was one of us, but you might not know who it was. So if you think about it, you kind of need to make a decision about which one of us it is, and then you can kind of guess that from looking at the slides today. But it's not just a random like mishmash of all of us together, like attention tries to do for you. And this is true for a whole bunch of different things, here. So a latent variable model, we have an observed output x. We assume that a continuous, we will assume that it's a continuous vector until the next section. And then we have a latent variable z generated from a Gaussian. And we have a function f parameterized by theta that maps from z to x, where this function is usually a neural network. So this is our generative, or this is our model, basically. And this is the model where we used in the variational autoencoder. And the reason why this works is because, and this was also one of the quiz questions. The reason why this works is because even if we sample from this z here, with an arbitrarily complicated neural network, we can map this into any other function distribution, right? So, so we take our z, which is randomly distributed according to the according to the normal distribution, and we run it through a neural network, and we can get any arbitrary probability density function, with a few exceptions about it being smooth, et cetera. But because of that, you know, having a latent variable be Gaussian is fine. It's no problem. So is that clear? Was that clear to everyone? Yeah. Okay, so z here is a latent variable, a latent random variable, and x is a deterministic variable that follows from z. So what is our loss function? We'd like to maximize the corpus log likelihood. So this is our loss. So over the entire corpus, we calculate the log probability of all of the examples and add them together. And that gives us our corpus likelihood. And for a single example, the marginal likelihood is integrating over this variable z. But because, how many people here are kind of familiar with Bayesian methods with conjugate distributions? Do people know about this very much at all? Well, that's actually not very many hands at all. I thought I was going to have more. Okay, I'm sorry. Because I'm old, I'm going to give a little bit of background. But before variational autoencoders and neural nets and stuff, there was an idea that if you take this prior distribution and multiply it by this posterior distribution, and you can get a distribution of the same shape, then you can, then it's very easy to do inference and integration and stuff like that. So, for example, if PZ is a Gaussian distribution in this posterior distribution here is also based on a Gaussian distribution. If you multiply them together, you get another Gaussian distribution, or something like that. So if you do that, you can actually integrate over this thing and calculate things exactly. So that's the idea behind a conjugate prior and posterior distribution. But the problem is now, while we're doing this PZ as a Gaussian, this thing on the left side is now a complicated neural network. And there's no way we can integrate over this appropriately, which means that we have to resort to some sort of approximation method. And the approximation method we always resort to, because it's very easy to do, is sampling. So we take a sample, a set of samples randomly distributed according to this prior, which happens to be a Gaussian in the normal variational autoencoder, and then we sum over this. And actually, sorry, I think I forgot to divide by the in this formula. I forgot to divide by the size of the sample, but you need to divide by the size of the sample also. So the problem that the variational autoencoder is trying to solve is that straightforward sampling is inefficient. So if you think about it, if the thing on the left is our distribution, and we have our current data point here, this is the one that we want to talk about maximizing the likelihood of. there's only a very small portion of this space in Z that actually gives it a decent probability, right? So, so this space in Z maps into this space in X. But for the great majority of the samples that we could draw from this distribution in Z, basically we're going to get almost no probability when we calculate the probability of X. So this is going to be a bunch of wasted sampling that isn't useful for us. So was this clear to everyone, or are there any questions? Or yeah, okay. So the solution to this in the variational autoencoder is an inference model. So we have another distribution that predicts which latent point produced the data point using an inference model that looks like this. And we acquire samples from the inference model to do more efficient training. So the basic idea is, given this point X, given that we know we want to optimize this point X, we use the inference model to predict which point in the space Z we are going to be using to calculate our the output. And the reason why this is called a variational autoencoder is because it encodes with the inference model and then decodes with the generative model that we're using. So the encoding goes from right to left on this thing, and then the decoding goes from left to right. But in reality, it's not a encoder decoder. It's just a generative model. But at training time, we're using something that looks like an encoder in order to make training more efficient. So there's but unfortunately, using this inference model leads to a disconnect between the samples and the objective. So we want to optimize this expectation here, the expectation according to the actual distribution over Z. But instead, if we're sampling according to Q, we're actually approximating something else. We're approximating the distribution according to the expectation according to this inference model. So you'll notice that the bottom and the top things here are different because they're integrating according to different distributions. So how do we resolve this disconnect? The interesting thing about the VAE is they came up with this very elegant solution to basically convert this in a way that makes it possible to calculate efficiently. So we start out with the definition of the KL divergence between these two distributions, which is just this. And then we convert this equation with the Bayes rule, which basically gives us something like this. There was a thing, kind of a magical thing that said we rearrange and negate everything, and then suddenly we get a new distribution where if you went through the math, you could see that what they're doing is they're moving everything around. So actually, the alignment between these equations was a latent variable that I had to infer from the text, but I was able to do that. And then based on the definition of KL divergence, you can then contract all of these things together. So this is on the slides, but basically the point is that we can go from this definition of KL divergence that we know beforehand, and we can come up with this objective down here. So that doesn't mean a whole lot until you go to try to interpret what this VAE objective is saying. So basically what this is saying is the left side is more or less what we want to optimize. So this is the marginal likelihood of our latent variable x. This is what we said we wanted to optimize in the first place, right? This is our normal loss function. Then there's another term here, which is basically the accuracy of the inference model. It's the KL divergence between the inference model and the actual probability of z given x. So Understandably, we would like our inference model to be accurate. That's a good thing, to have an accurate inference model because it will make training faster. So this objective is basically optimizing that. But the right side is something that we can optimize. So as I said before, the expectation according to Q of the posterior, this is exactly the thing that I said we could do by taking the inference model and sampling according to the inference model and then calculating the probability, the posterior probability. So this is exactly the thing that I wrote here. So that's what we can do by sampling from the inference model and calculating the probability. And then the second thing is the KL divergence between the inference model's prediction and the prior probability PZ. So if we think about it, on the right side of the equation, the first element of the right side of the equation is basically the thing that we can calculate efficiently, the posterior likelihood that we can calculate efficiently. The second thing is a penalty for when Q diverges from the priors. So we have this thing that's kind of pulling in two directions. One direction is towards maximizing the likelihood and using the inference model in an efficient way to maximize the likelihood. The thing on the right side is a thing that's saying you don't want your inference model to move too far away from the prior. So yeah. Did you have a question? Yeah. It's not the marginal likelihood, but according to like Bayes' rule, this is usually called the likelihood. It is a posterior probability of x given z, but yeah, I should call it the likelihood. That would make it easier. So yeah.
I missed the time of question, but can you tell me again why we should sample Z directed from the PZ is inefficient?
Oh sure, yeah. So basically, we have our probability P of x given z. And the idea is that there's some connection between the latent variable z and the variable x. So given the variable z, we are able to predict x with a higher probability. But this is only true for z that correspond to x in some way. So if we think about a function that's basically going from this and kind of expanding it into a circle, then only points on the left that will appear in that particular place on the right side, or that correspond to that particular place on the right side, will give any sort of high probability according to this. So if we just randomly sample points from here, most of the points here will have a probability that's extremely close to 0 for this. So if we just randomly sample, almost all of our points will have a probability of 0, which means we're just wasting time. So that means we really want to get point Z that will give a non-zero, or a probability that's not extremely close to 0. Okay. Any other questions? So, yes. Okay. Yeah.
I'm just wondering, is it guaranteed that the Q of Z given X, so the Q of Z given X that we find by maximizing the right-hand side of the equation gets closer to P of Z given X on the left side? So the KL divergence term on the left side. Does that become 0?
It's not, it's no, because you have two conflicting terms, basically. You have the px term, and you have the other term. And in some cases, actually, that will that's actually a good question, but I think the answer is no. I'm going to talk about a tangentially related topic in a moment, and I actually haven't thought about the answer to that question, but I might realize as I'm talking. But one very important thing to think of here, and I'm going to talk about this in detail in a moment, is that we have two terms here, and these two terms are in conflict. Basically, you can't optimize both of these ideally, because one will pull in one direction, one will pull in the other direction. So you're finding a compromise between the two. Yeah.
One thing, so going back to the assumption of VAE, that's one sort of a probability distribution is definitely better than random sampling. That random sampling gives too many zeros when you start. Is it necessarily the case, say like if you have a ring distribution and you throw in a Gaussian distribution, that actually might be worse than random? Is that possible, or I sort of have a little bit difficulty of understanding why is it always the case? Why is throwing an assertion, a probability assertion there is always better than random?
What is better than random? I'm sorry, I didn't understand the question.
You were forming the question as a VAE trying to solve the assumption of say like the ring distribution. When you start with random, you think there are too many zeros, and my question is basically, is assuming a certain type of a distribution necessarily better than randomly sampling?
So we're not, just to be clear, we could randomly sample from this Gaussian distribution and just optimize over that without using any inference model at all. If that is the case, if that's just as good as anything else, our inference model will basically learn to create this, we'll learn to generate basically a zero mean unit variance Gaussian distribution. So the inference model also could say, I just want to sample from this distribution as is, without doing any tricky stuff depending on what our value of x is. And in fact, it does that pretty frequently. So I'll explain about this in a moment, but I think that might answer your question. Okay, so I'll move on to the next part. So are there any questions about this? No? Okay. So the next part, and this is another really clever thing about the variational autoencoder that kind of made it a very popular option. And the clever thing here is basically one of the bad things about models with latent variables is you need to do sampling, and sampling basically you cannot backpropagate through a sampling operation. There are a few operations in your neural network that you cannot backpropagate through. Sampling is one of them, and something like argmax is another one, because basically their gradients their gradients are zero almost anywhere, so you get no gradient as you backprop through it. This is the traditional way that you would kind of implement your variational autoencoder, which is where you use an encoder, your inference model, to predict the mean and the variance according to x, you then sample from this distribution where you calculate the mean and variance according to it. And then you use that sampled value in the decoder and calculate your value. And then the blue things are your objective function. But the problem is this red thing is something that you can't backpropagate through. So basically, you lose all of your gradient signal from the loss function up there, from your reconstruction loss. So the trick is a reparameterization trick, which is basically you move the sampling into the input of the neural network. And the way you move the sampling, by moving the sampling into the input of the neural network, you sample from a zero mean unit variance multivariate Gaussian distribution. And then if you multiply that by the covariance matrix and you add the mean matrix, you get something that's distributed according to the actual distribution. So let's say, sorry, that's the worst Gaussian ever. that was extremely embarrassing. Okay, here we go. So let's say we have something like this, where this is 0, basically. So we sample according to a round Gaussian here. Then we add the mean, which gives us a round Gaussian up here. And then we multiply by the covariance, which gives us the thing that we want. So basically, this shows that we don't need to do any random sampling according to a distribution that depends on the input, which means now we have this nice graph where we have the sampling over here, but we have a direct path from here to the output with no sampling operations, which means we can do backpropagation through this. So this is kind of, there's two beautiful things in the variational autoencoder. One is this reparameterization trick. One is the fact that we can sample according to the inference distribution to make it fast, and then by paying this KL divergence penalty, it can be basically the correct objective. So are there any questions or comments? Yeah.
Is there a common name to refer to the family of distributions that can be reparameterized?
I think any distribution can be reparameterized with a sufficiently large and deep neural network, right? So, not any, but yeah. So what I mean is basically anything where you can sample from a distribution and map it onto another distribution is a distribution that can be reparameterized, right? So the variational autoencoder itself is something that's relying on the fact that we can reparameterize distributions. So you could think of a really crazy variational autoencoder where instead of multiplying and adding, instead you had another neural network that, instead of this multiplication and addition operation, you had another neural network that took in this and then mapped it onto something. So you can basically have a, I think, arbitrarily complicated reparameterization function, as long as you have certain things like smoothness or very weak constraints. It's another question, like which ones can you do easily by like multiplying and adding and stuff. Those might be ones that are conjugate distributions. So that was exactly the thing that I talked about before. Where you do some simple manipulation to it and you move from your prior to your posterior or something. There might be a connection between conjugate distributions and this, but that's kind of another topic. Yeah.
So do variational autoencoders give us much interpretability about Z?
I'll talk about that in a little bit, and the answer is kind of yes. Yeah. Yeah.
Are there some other distributions that are commonly used instead of Gaussian?
I'll talk about one for discrete variables. In terms of, there's other more advanced methods for doing variational autoencoders that have more complicated functions mapping between them. I'm not super familiar with them. Chunting is, so you can ask her about the details. But yeah. So yeah. So I have an example here. The first example, this is the NLP stuff that I'm going to be the first NLP stuff that I'm going to be talking about. This is actually a piece of work that was done by Sam Bowman, who just gave the talk last Friday here. And somebody pointed out to me that I should have done this class 1 week earlier, so he could have given a guest lecture here, but unfortunately I missed the boat on that one. But I'll try to explain his work instead. So generating from language models. Remember, we can generate from a language model, any language model we have. So using ancestral sampling, basically what we do is we start out with a 0 vector, a 0 hidden vector in our LSTM, or we input the start of sentence symbol into our LSTM. And then we calculate the conditional probability of the next word. And the conditional probability, based on the conditional probability of the next word, we randomly sample a word. And then we continue doing this until we get the end of sentence symbol. And we can also do this when we want to generate something conditioned on something, like translation or image captioning. And this was the whole conditional generation class that I taught much earlier in this semester. So we already have a generative model for text. This is something to remember. So what are we going to do? We're going to make a generative model for text. This is going to be a different generative model for text, and it's going to have a couple nice properties. So the VAE-based approach to generating text is basically a conditional language model that conditions on the latent variable Z. It's like an encoder-decoder model, but the latent representation is a latent variable, and the inputs and outputs are identical. So what it looks like is we have basically our sentence X on both the input and the output. We have our inference model, recurrent neural network, that reads in this sentence one by one. It then, sorry, this is a little bit misleading. So what it predicts is it doesn't actually predict the latent Z directly, but it predicts the mean in the variance of the distribution over the latency. So instead of a normal encoder-decoder model, which basically outputs a single vector, what it's doing instead is it's outputting mu and sigma, and then from this mu and sigma, you can sample a latent vector that represents this this sentence. And so it's actually a quite straightforward application of the variational autoencoder idea to text. The only thing is that our encoder and decoder are both RNNs. That's really the only difficulty about this. So there was a question just now about the interpretability of models here. So one of the motivations behind this model, as you know, we already have encoder-decoder models. We already have generative language models. Why would we want to go out of our way to do this variational autoencoder model? So one motivation is it allows for potentially a more consistent latent space. So you can find this from 2 good examples in the paper. So in the standard encoder-decoder, if you, sorry, this is kind of small, but if you look at this, the thing on the top is I went to the store to buy some groceries, and then horses are my favorite animal. And what they did was they basically took the vector, they had an encoder-decoder model, and they took the vector from the encoder for both of these sentences, and then they interpolated it. So they gradually moved between the two vectors. I see some people squinting. The slides are also online if you want to look at them on your computer. But what you can see is I went to the store to buy some groceries because I stored to buy some groceries. I were to buy any groceries. Horses are to buy any groceries. Horses are to buy any animal. Horses are the favorite any animal. And you can see that these kind of contain the content of the original sentence, but they are, the intermediate sentences are not actually sentences. They're not well formed. On the other side, if you go to the right, they have, I want to talk to you. She didn't want to be with him. And you can see the interpolation between the VAE learned vectors is, I want to talk to you, I want to be with you, I don't want to be with you, in quotes. I don't want to be with you, not in quotes, and she didn't want to be with him. So you can see the intermediate vectors are more, or the sentences generated from the intermediate vectors are more consistent. And there's another example on the bottom. So why is this? Any ideas? So yes, that's true, but more, do you have a more specific
because the distribution that we are generating, clear divergence makes sure that it is more close to the original distribution, but there is nothing like that in the standard.
That is pretty close. Yeah.
We force the latent distribution to be a Gaussian with no non-diagonal correlation, so there be no correlation between the individual coordinates of the latent vector.
I'm trying to think if that actually explains what my personal idea about why this works is. But that might be true, that might not be true. So the two comments were the KL divergence forces us to be close to the original distribution, or there's no non-diagonal correlation between the two. My personal explanation, basically, is we're generating these vectors from a distribution, or these latent vectors from a distribution, and we're kind of randomly generating them from this distribution. In other words, our model has to be able to handle vectors that get generated anywhere in this space. So if the model has any places in this space, that are essentially wasting probability that don't generate reasonable looking sentences, it becomes a waste of the model's capacity, and it will pay a penalty for this. So if for some reason this part of the space just generates garbage sentences that you would never see, the model will get a worse score than if it's using all of this space efficiently, I guess. And because of that, if you get to, if these sentences in here get a reasonable probability according to the prior distribution, if it's generating wrong things from there, it will not work. On the other hand, for the standard encoder-decoder model, there's no such penalty when that happens. So I think that's my interpretation. If somebody can prove that's wrong or not wrong, then that'd be great. But that's my interpretation. The second thing is simply it might be more robust to noise. If you think about it, more robust to noise in the latent distribution. If you think about it, we're adding a noising term, basically. And because there's some random noise, this often helps, even in non-VAE models. So we have an example of this. It's a super simple modification of the standard encoder-decoder model, and I think Hector is going to talk about it.
So this piece of code is taken from the previous conditional LM code. So most of the stuff are the same. We read in data training and testing or whatever. Let's go to the actual calculate loss part. One thing we need to do is we are building RNN to RNN, and we have a latent variable z in between. So for the first RNN, we first get its output, the source output. Now, as Graham said, we need to get like two variables from this RNN. We need to get mu and we need to get a sigma. And all we need to do here is we use the power of natural networks. We put it into an NLP. So we define the NLP parameters. Here we use just one hidden layer NLP, so one W and one V as an output layer. So by putting the source output into the MLP, we can get the mu. Let's say this W, V, and B, and this MLP can give us mu, and another MLP can automatically give us the variance. So the trick, the implementation here, I'm using a log variance, which seems to be the common trick that people use, because you don't have to explain your variable to be sigma. You can say the MLP output the log sigma, because you don't know what the MLP is doing anyway. So let's say it's outputting a log sigma. And then we can compute the KL divergent loss. So for the KL part, you can see this, you can find this formula in the original VAE paper appendix. So between two Gaussian, and one of them is a zero center and one is a mean. So we just calculate this value, which will be the KL divergence between our model generated mu and the actual sampled one. So here you see we use the log of the sigma, so it's log. We directly use it. Here we use the original covariant matrix, so we do exponential. Now there's a reparameterization trick, which computes z for us. So that's pretty simple by because we have the mu and log variance of that small circle down there. No, we don't have that. We can sample one small Gaussian circle down in the center 0, and then we add the mu and multiply by the variance. Here, because when you see the actual formula, you will have a square root of that. So here we multiply by the log variance by 0.5. So that's the simple part about using a log variance. You can skip square root. But anyway, you will do the exponential back anyways. So it's your choice to use a log variance or the original one. So now we get back this by multiplying that and then plus that mu. So here we get a z. The last part is easy because we can say the z to be the input for the next RNN. Here I designed this z to be exactly the dimension matching the output RNN. There are also implementations that you have to pass the z to another MLP to match the dimensions. You don't want the dimension of z to be too high for some reason. But in this case, I just designed this MLP to make the z to have exactly that dimension. And the last part, and the rest of them will be easy. Just put a z inside there here and get a very traditional LSTM for the target part.
Cool. Any questions about this? I think, if anything, you could see that this is actually really quite simple, despite the, the fact that the math in the original paper in particular is relatively intimidating. The procedure to run this is super simple and actually quite efficient. So it is good. So there's a couple things you need to be careful about, which is that variational autoencoders are not the easiest thing to train. It's especially the case for text that you need to be very careful. So one of the reasons for this is, of the two components in the VAE objective, the KL divergence term is much easier to learn. So let's take a look at this. So for this KL divergence term, we can just set the mean and the variance to be exactly the same as our prior. In other words, we can set the mean of Q to be 0 and the variance of Q to be 1, and we get a 0 KL divergence for free. So because of this, basically this KL divergence term is trivial to learn. So if you put this into a standard neural network, it can learn to optimize the right side very easily. While on the other hand, the left side requires a good generative model. And as I'm sure you know from looking at the class, creating a good generative model of language, for example, is not as difficult. People still research it, yeah.
So where do we get our prior PhD? Is it just set?
This is usually just set to a Gaussian with 0 mean and unit variance, yeah. And the reason why we can always do that is because we expect the model P of x given z to be a large, complicated neural network that can simulate any function. So what this results in, much of the time, is that it results in the model learning to rely solely on the decoder and completely ignore the latent variable. So it basically learns a good language model for P of x, but it doesn't even use z at all. Because it learns to basically minimize the KL divergence on the right side and then just learn the generative model without using the z at all. So one solution to this is called KL divergence annealing. So that basic idea is we multiply the KL term by a constant lambda starting at 0, then we gradually increase this as training goes on. I said we gradually increase it to 1. Sometimes we actually gradually increase it to a value that's less than 1, although that doesn't give us the true VAE objective. As a result, the model can learn to use z before getting penalized, and you can actually see this in the graph in the paper for using this for text generation. So we start out with the KL term weight of 0, and after when the KL term weight of 0, it learns to basically learn an inference model that gets a very, very high KL divergence. So it learns something that's very, very different from the prior. And then we gradually introduce this KL term. And after we introduce the KL term, the KL divergence drops drastically, but it doesn't drop all the way to 0, because the generative model has already learned how to use the latent variable. So it does a little bit better with the latent variable than without the latent variable. So this is one trick. This is very important. It adds a couple hyperparameters to your model, but if you do this, it tends to work. Another trick is to weaken the decoder. So the KL divergence method before, or the KL divergence method that I talked about before, does tend to work, but theoretically it's still problematic. So basically this paper up here, what it has shown is that if you can generate things perfectly or very, very well without using z, the optimal strategy is to kind of ignore z. And so in a way, this method here is kind of relying on you to not optimize your model properly, in a way, which is possible because neural networks fall into local minima. So the solution, another solution, is to weaken the decoder that calculates p of x given z, so that you have to use z in order to do a good job. So one example of how you can do this is using word dropout. So what this means is instead of inputting all the previous words that you've already generated, you drop some of them and just set the input vector to 0. And by doing this, you're making your decoder weaker. So it really has to rely on the information that's encoded in Z in order to do a good job of calculating the probability of the output. Another example of something that has been done is to use a convolutional decoder with limited context. So this is, you can think of this as instead of using a full RNN, which can basically remember all the words that you've done previously, you're only relying on the past couple words. And if you're only relying on the past couple words, it'll be like a regular n-gram model. It'll be much weaker than your nice LSTM language model. So it has to use the Z to basically remember the content of the sentence. So this is another trick that has proven useful. Any questions about this? No? Okay. So let me move on to the next part. This is actually a pretty interesting part. I'm not going to talk about everything related to this in this class, because actually I'll be talking about this over the next 3 classes also. But I'm going to talk about a few tricks that are useful with regards to handling discrete latent variables. So many variables are better treated as discrete than continuous. So obviously the part of speech of a word, the class of a question, speaker traits like gender, etc. Usually these can be put into one discrete class without having a continuum between them. So how do we handle these? So one way you can do this, which is not, this is the equivalent of basically taking the integral over your entire latent space of Z latent variables. So we just enumerate over all configurations of these discrete latent variables and calculate something here. So if the number of possible configurations for Z is small, we can just sum over all of them. So let's say we had an example where we wanted to create a generative document classifier, for example. So we have a document classifier where we want to classify a document into one of 10 topics. If it's only one of 10 topics, we could conceivably just enumerate all of those topics and calculate the probability based on all of those topics, and that would be no problem at all. This will only work when the number of configurations of Z is extremely small. It will obviously not work if the number of configurations is exponential, like in structured prediction problems. Another thing we can do, like we always do, is sampling. So we randomly sample a subset of the configurations of Z and optimize with respect to the subset. There's various flavors of how we can do this. So we talked about minimum risk training we talked about minimum risk training before. This is good for encoder decoders. There's also reinforcement learning in the next class. One of the problems with sampling, as always, is that we cannot backpropagate through it, and it results in very high variance. You would also have to come up with an inference, basically an inference model for these latent variables, which is a little bit more complicated than the original case, but it's not too complicated. The final thing that I would like to talk about with respect to discrete latent variables in a little bit more detail is We can also do re-parameterization tricks for distributions over discrete latent variables, which allows us to basically do backpropagation through discrete latent variables with a qualifier that I'll talk about in a second. But the idea is as follows. So the way we normally do sampling in a categorical distribution is we have this categorical sample function, which takes in our probability distribution P of z given x, and we randomly get an ID according to this distribution, where z hat is maybe a one-hot vector representing the ID that we selected. So you can do this in NumPy. You can do like np dot sample, was it, or random choice? I forget the NumPy. What's the NumPy function for this? Anybody? Choices. Okay, NumPy.choices or something. So we know we can do this, but this function is not. You cannot backprop through it easily. Luckily, there's a reparameterization method that's very similar to the reparameterization method that was used for it's very similar to the reparameterization method that was used for the regular VAE with the Gaussian variables. And it looks like this. I actually I've made a mistake in this slide, and I'll explain it in a second. Sorry, I just realized there's a mistake here. But the basic idea is you take your log probability, and then you also take a random variables, a vector of random variables, calculated according to the Gumbel distribution, which I'll explain in a second. And then you don't take the max, you actually take the argmax. So the argmax will select the value with the highest, or select the element with the highest value and turn it into a one-hot vector. So this is, and then the Gumbel distribution is basically negative log of the uniform. It's the negative log of the negative log of the uniform distribution. So don't ask me why this happens to be true, but the Gumbel argmax and the categorical sample will give you exactly the same result, or they'll give you exactly the same thing. And actually, I don't know how Gumbel came up with this magical distribution like this, but these can be proven to be equivalent. The problem here is, I mentioned we're doing categorical sample, and this we cannot backpropagate through. We're also doing an argmax. Note that I made the mistake on the slide, and that should be an argmax. But we're still doing an argmax in the reparameterized method. And if you remember here, these are the two functions that I said we could not backpropagate through. So we still cannot backpropagate through the reparameterized version. So yeah, I made these slides too late last night, so I'll go back and, or not last night, but I made these slides in a rush, so I'll go back and fix that. But one way that we can get around this argmax is, instead of taking the argmax, what we do is we take a softmax. So basically it looks like this. So we change the argmax into a softmax, and we take the variables here, and we exponentiate them by 1 divided by a temperature. So it might not be immediately clear what this is doing, but basically as the temperature approaches 0, we'll approach the argmax. So this, as we lower our temperature to 0, this will become equivalent to just sampling. And there's a really nice figure in the paper that demonstrates this. So if we look at the categorical distribution, it looks like this. If we do the Gumbel softmax trick with a temperature of 0.1, it looks almost exactly the same as the categorical distribution. But as we gradually adjust this by adjusting the temperature, we get something that becomes more and more flat. So the idea here is that we can do something very similar to the reparameterization trick and still backpropagate through our models that have these discrete random variables. And we start out with a relatively high temperature, and we gradually move that to a lower and lower temperature to approach something we get from sampling. Yeah.
I think you can also do what they call straight through Gumbel softmax, where basically you take the argmax during the forward pass, but you keep the relaxation for the backward pass.
Yeah. So this also works. Yeah, I probably should have put a slide on this. So just to repeat the comment, there's a thing called the straight-through estimator. So the straight-through estimator, basically what it does is during the forward pass, it takes the argmax. During the backward pass, it makes it, it takes the gradients as if you didn't take the argmax, right? Is that the appropriate summary? So this is another way, and the advantage of doing this is instead of getting this kind of mixture type thing, you get a single decision. You get a single like argmax sampled decision. The single argmax decision is good because, as I said, you can't mix your TAs and your instructor about who wrote the slides. So mixing, this is basically saying you can mix your discrete decisions. You can mix together the TAs and take the average of the TAs and get some super TA or some mediocre TA that's worse than all three of them combined or something like that. But the straight-through estimator says on the forward pass we'll do it, we'll choose one, but on the backward pass we'll backprop. The problem with that is it's not a correct estimator, and it's not guaranteed to converge, or not guaranteed. It's not an unbiased estimator of the actual probability distribution. So I will go. We're very short on time, so we'll go very quickly through some application examples in NLP. I'll take questions at the end if there's still a little time, but I'll just go quick. So there were a couple models, a couple people who've done models for documents. This is very similar to the models for sentences, but you do it, but it will be a more consistent space. There's another one for question answer selection. Why do we want to treat these as stochastic random variables, or as latent random variables instead of just a vector? For documents, maybe a more consistent space. For question answering, more regularization. There was another paper that came out recently that was kind of interesting, which is it's a latent variable model for text generation. The interesting thing about this is it actually combines this with adversarial learning, which I will be talking about next Tuesday, I guess, that allows you to basically create latent variables that are more controllable or more interpretable, which is a thing that we talk about later. This is another one that by us that we talked about before. This method has a combination of latent continuous and latent, not maybe binary, but latent categorical variables that can do semi-supervised or supervised learning. So if you want to combine both in a generative model, this would be one paper that you could take a look at. Another thing, this one is perhaps, this is also quite interesting. You can have latent variables that are not latent continuous variables, but they're latent sequences of symbols. So the idea is basically we have something that looks like this, where we have an encoder that takes in a sequence of symbols in the source. They're calling it compressor here, but basically what it's doing is it's predicting a sequence of latent symbols, and then we have a reconstructor, which takes in these latent symbols and reconstructs the output. So there's a couple of methods for this. This particular method here that I cited, they use it for summarization. So this is kind of interesting. You can drop words. The idea is you can drop the less informative words in the source and still have a good latent representation that allows you to reconstruct the target. And if those symbols in the source are informative, then they're probably also a very good summary. More interestingly, I'm not sure what to think about this work yet, so we'll see how what happens in the next couple of years. But I think a lot of people are interested in this. There have been attempts to kind of discover language. So this particular work here, you show an image, and then you ask the learner to basically output a sequence of symbols that describe the image, and then it reconstructs, or then it has to choose which of the images is correct. So if you have 3 images of pizza, for example, it has to learn symbols that allow you to discriminate between which of those 3 images of pizza the original representation was talking about. And one of the, I guess this was probably one of the outstanding or best papers at EMNLP, but basically this paper here analyzes what happens when you learn with these models. And their conclusion was that, sure, they may be able to learn a sequence of latent symbols, but this sequence of latent symbols doesn't really look a whole lot like language. And you have to use a lot of other tricks to kind of make it look something like we see in human languages. So, regardless, I think this is a pretty interesting direction that we might find more stuff in the future. And then a final one, there's a number of methods that incorporate kind of latent variables in recurrent models. I think a lot of people will be very interested in recurrent models because they're good for language. And this is one reference to this that basically predicts the latent variable based on the state of a recurrent neural network. I think there's a lot of other ones after this, so you can look up the additional references. But this is another thing that you might have to take a look at. Okay, that's all for today. Are there any questions or comments or anything? Okay, if not, we'll finish up. Thanks a lot.